Okay, so we are talking about really KF and formation of complex ions and the equilibrium that goes with it. So as we finished up on last time there, again, the ligands, they do come on basically one at a time. And for each of those steps, it does have an equilibrium sort of value associated with it sometimes. When we add up all the steps together, in the case that we looked at the end there, the adding of the four chlorides, it does basically give us the Kf by multiplying each of those K values together. So very similar to what we did, in just basic sort of equilibrium, where we basically multiply equilibrium constants together when we add equations. So what we're going to do now is we're going to go through an example here of sort of a KF type problem. And again, we're going to see slightly how it's different than a normal sort of equilibrium problem and how it's sort of similar as well. So we'll talk about kind of both of those things as we kind of go through it, some of the things that we do in these type of problems that maybe we don't do in other problems, and a couple of reasons why we sort of do those things. All right, so let's take a look here at this example. So here we take 0.2 moles of copper 2 sulfate is mixed with a liter of 1.2 molar ammonia. What is the concentration of the copper 2 at equilibrium? So basically here in this problem, we're forming a complex ion, obviously, between copper and ammonia. And it makes our copper and ammonia complex ion on the other side there. Again, our tetramine copper 2 ion on the right hand side. Coordination number there 4. So what happens when we do these problems? Well, a couple of things. We basically do an ice table. So obviously we'd probably imagine, since there's K involved, that we do work it very much like a normal ice table. But there are a couple of things that we do a little bit different, and there's some assumptions that we make when we do these type of problems. So let's take a look at sort of how we go about this. So let me just find a page here. There we go. We'll just rewrite the problem here and borrow that. Okay. So in this particular case, we're going to assume that we have a liter. So we're going to convert everybody into molarity here in sort of the mixed solution. So we'll assume we have 1 liter total. So that will give us 0.2 molar copper 2. Again, that is coming from the copper 2 sulfate as the only source of copper in the solution. Again, the sulfate here is really a spectator ion, so not really doing much in terms of the overall sort of reaction. Now, obviously, this is the molarity of our ammonia. So we will start our ice table here kind of like normal. We will do our initial will be 0.2 molar. Our NH3 will be 1.2 molar. And initially, we could assume that we do not have any of the complex ion that is there. Now, what comes next is a little bit different, and it really is based off of the other piece of information that was given to us, which is the KF value. KF value is 5 times 10 to the 13. When we look at that KF value, we definitely see a value that is really, really large. Yeah, times 10 to 13, that's a pretty big number. That is a very large value. And that typically happens when we're doing sort of KF problems. We typically do run into large values of K. And because of that, when we do these problems, we really do make a couple of assumptions. And the very first assumption that we make is, because this value is so large, all of the metal will end up in the complex ion. And why is that? Is because obviously with a value of K that large, pretty much, even though it's a reversible reaction, we could probably safely assume that that reaction is almost a one-way reaction in this case. Because it is so large, we could assume that the value pretty much of of that KF is going to force really that reaction all the way to the right. So what does that mean? Well, what that affects is we assume that all of the metal, which is the copper in this case, will get pretty much 100% used up. And what that means is the change here, how we normally do X's. We actually know what the change is going to be. The change is going to be, in this case, the amount of copper 2, as the KF value tells us is going to really force that thing all the way to the right. And we would expect that pretty much all of the copper 2 gets completely used up. So we will say this is minus 0.2. This would then be minus 4 times 0.2. And this would be plus 0.2. Any questions on that there? Now you may be asking, what's the deal here? The deal here is, I'm just going to do it to the right. If we were to just do our X's, for example, so if we were going to do for our change, I'll just put the change here. If we were going to do our X's, we would normally do minus X, right? Minus 4X and plus X. And that is essentially what we did here. This is basically minus X. This is basically minus 4X. And this is basically plus X, except that we already know what X is. So we're just kind of putting it into our change line. Any questions on that? And again, that's why the 4 is here. Just like in a normalized table, right? We do need to take the coefficient into account. Otherwise, again, we're going to end up with the wrong answer. All right, so I'm just going to kind of clear those out so don't get too confused here. All right, that means that when we reach equilibrium at this point, we normally carry everything down, but we could just really do the math at this point. And that means at equilibrium, like our assumption was, that pretty much all of our assumption over here, assume, all of the copper is completely gone, is now completely pretty much been tied up in our complex ion. We then would take for our NH3 1.2, which was our initial, minus basically 4 times X. And that's going to get us 0.4 here. And we would have 0.2 here. Any questions on that so far? Now, if we were asked a question like, you know, what is the concentration of NH3 at equilibrium? The answer would be 0.4 molar. If we were asked what is the concentration of our complex ion at equilibrium, it would be this number here, or it would be 0.2 molar. But in this particular case, we were actually asked what is the concentration of our copper, right? Which is this. Now, clearly, if the answer was 0, that wouldn't be much of a problem to do. And the answer actually is not 0 in this case. And that is because even though we make this assumption that pretty much 100% of this copper 2 gets pretty much tied up in that complex ion, it is still ultimately, even though we kind of consider it a kind of one-way street, it is still a reversible reaction, which means that even though 100% of it is pretty much in that complex ion, some of the complex ion will break back apart. A little. And that should produce some copper 2 ions that would be in that solution. Now, the second part of the assumption is we assume that all of the copper 2 is going to be tied up in that complex ion. The second part of the assumption is, although most of it will be tied up, some of it will break back apart into free copper 2. And it should be a small amount. like really small amount. We should have really small amount of copper 2 that's still left. So what do we do at this point? Well, even though we zeroed out the copper 2 in our ice table, we then go back and basically call it X because it's what we want to basically solve for. How can we solve for the copper 2 at equilibrium? Well, at this point, we can use our equilibrium expression, our KF expression, which is our products divided by our reactants. Again, remembering not to forget to take, in this case, the NH4 to the fourth, and that equals our KF, which is 5 times 10 to the 13. We could do this because from our first ice table, we now have the equilibrium constant or concentration of NH3. We also have the equilibrium concentration of our complex ion. We originally had the KF given to us. So that's going to allow us to solve for the copper 2 concentration here. And in this particular case, that would be 5 times 10 to the 13 is equal to our 0.2 up on top, which is our complex ion concentration at equilibrium, divided by the copper 2 concentration, which is what we're looking for, times our NH3 concentration at equilibrium, 0.4 to the fourth. Basically, what happens mathematically speaking is these two guys switch places. So that ends up giving us a copper 2 concentration that is equal to 0.2 divided by really our KF value times our 0.4 to the fourth. And if we put all of that in there, we end up with looks like a 1.6 times 10 to the minus 13 molar would be the equilibrium concentration of free copper 2 in that solution. That is obviously a super small amount of free copper 2. Basically, there is no copper 2, but there is technically still a super small smidge of free copper 2 ions. Again, pretty much in that solution, you got 100% really of the copper tied up in this complex ion. We'll just do a real small corner. Really small corner, you got about that much of free copper 2 ions basically floating around. But again, a majority of it is that complex ion in that particular case. So this validates our second assumption that the amount really of free metal when you're dealing with complex ions is going to be a relatively small number. Any questions on that calculation there? So this tells us, like we've been talking about, that really, the formation of a complex ion is really favored, right? It really wants to occur when we do these type of problems. Okay, so why don't you try one here? So take several minutes here and see what you come up with. In this case, we pretty much want to know what is everybody's concentration at equilibrium in the formation here of our complex ion. Here we have a stepwise formation that's happening of our complex ion. So take some moments here, some minutes, and maybe we'll talk about it here in like 10 minutes or so, or 5-10 minutes. Again, you were looking for a lot of answers. We're looking for the concentration of silver at equilibrium, our AgS2O3 minus, or AgS2O3 3 minus, and a whole bunch of everybody's sort of concentrations. So in this case, we're mixing these solutions together. So I'll give you a hint. You want to find the concentration of these ions in the mixture solution. and then proceed just like we just did there. There's a couple of different ways you could kind of proceed in this case, so we'll talk about those as well. So why don't you first take some time here and see what you come up with, and then we'll see if hopefully everybody's on the right track. So we basically want to find everybody's concentration at equilibrium, silver's concentration, sort of our intermediate step, if you will, until we get to our final sort of complex ion. We're mixing a couple of things. We're mixing some silver nitrate. We're mixing some sodium thiosulfate, so our Na2S2O3. Now, we have this, again, stepwise complex ion formation. So we have basically, as we talked about, the first ligand coming in, which is our S2O32 minus, followed by the second ligand coming in to really our product of the first step, again, giving us sort of our overall reaction that's happening when they come together. We could actually get that overall reaction by simply adding both of these guys together. And if we add both of these steps together, again, this guy will cancel, and that will leave us basically that a silver ion is going to pick up two ligands here, S2O32 minus, and going to form, again, our complex ion here in this particular case. Now, we can also, if we wanted to, get the Kf for this complex ion formation. Again, we would take K1, in this case, times K2, which, for reference sake, is 7.4 to the 8 times 3.9 to the 4. Gives us, we'll call it, I don't know, 2 points. What we got there? We'll call it 2.9 to the 13. Sounds good. 2.9 times 10 to the 13. Any questions on that so far? So the overall process that's really happening is really what we got going on there on the bottom is, again, those two ligands being attached to our silver ion. So what we really need to know is what are our initial concentrations of our silver ion and also our S2O3. And we're going to get that from really this guy, which is our source of silver, and this guy, which is our source of, basically our source of S2O32 minus, this guy being our source of the silver ion. So remember that we really want their concentrations after they've been mixed together, right? So that's how this process would occur. You dump them both into like a beaker or something like that, and that's going to basically allow us to start this reaction and get our concentration in the combined solution. So first off, if we did our silver ion, we basically can use M1V1 equals M2V2 here. So we would do something like M1, which is 1 times 10 to the minus 3, times our V1, which is 150 milliliters, divided by our V2, which in this case is the total volume. So again, here we're dumping 150 milliliters of the silver nitrate. We're also dumping 200 milliliters of our sodium thiosulfate, giving us a total volume of 350 milliliters. So that's, again, where that number comes from. We don't have to convert out of milliliters because they will cancel here. And that will give us an opening concentration for our silver of 4.29 times 10 to the minus 4. Any questions on that there? That obviously is because when this breaks apart, silver ion and a nitrate ion, it's again a 1-to-1 relationship between those concentrations. So it is the same. Same thing here. We'll do this for our S2O32 minus, taking our 5 molar, which is our like M1, our 200 milliliters, which is our V1, also divided by our total volume. Once we throw it in there for our mixing, milliliters will cancel. Going to open up with a 2.86 molar for S2O32 minus. Again, because when this breaks apart, you get basically 2 sodiums and 1 of these guys again, a 1-to-1 relationship between those guys. So that would also be the concentration there of the S2O32 minus. Any questions on that so far?
I have a quick question. Maybe I didn't hear it, but how did you get the 4.29 times 10 to the negative 4?
It would be by doing this calculation up here. So we took 1 times 10 to the minus 3 times 150, and then divided by 350.
Oh, okay, gotcha. Thanks.
Yep. And that would also be how we got to 2.86 by taking 5 times 200 and divided by 350 here. Other questions? Okay. All right, so now that we have really sort of the initial concentrations of our silver and really our ligand in our solution, we can really, if we wanted to, focus in here on the overall reaction that's taking place. And that's what we're going to do. So we're going to do a nice table very similar to sort of what we did previously. Again, we're going to be looking at the overall reaction here, which again is our silver ion plus our couple of ligands coming together to make our complex ion. Because it is a complex ion, and again, because of those Kf values like we talked about earlier, we can assume that all the silver in this case will get used up. Again, that's basically one of your sort of constant assumptions that you make when you're doing these sort of Kf problems and sort of complex ions problem, that all the metal, which in this case would be silver, will be tied up in that complex ion. So initially here, we're going to use those concentrations we just calculated, which was 4.29 times 10 to the minus 4. This guy was 2.86. And again, initially that is going to be 0. Because of our assumption, we will assume again in this case that our silver will be completely used up. We will then again have to take in our coefficient into account and times it by really our X value. And again, that's basically what the metal turns into here is our X value. And this will be plus 4.29 times 10 to the minus 4. That means when we reach equilibrium, as we would predict, we would have used up all of our silver in terms of it ending up over here in our complex ion. We will end up with 2.86 for this guy at equilibrium and 4.29 times 10 to the minus 4 for this guy at equilibrium. Any questions on the ice table there? So actually from this very first sort of ice table that we just did, we actually got a couple of answers we were looking for. So if we go back, we just got the concentration of one of these guys here. Actually, I was right here, so it won't be so all over the place. I'll put it over here. So from this first ice table, we could see that the concentration of S2O32 minus at equilibrium is 2.86 molar. We also see that our complex ion, when we get to equilibrium, will be 4.29 times 10 to the minus 4 molar. So we do have a couple of things given to us. We still want to find, we still want to find this guy. We still want to find really this guy's concentration. So at this point, as I mentioned earlier, there's actually a couple of approaches you could do. I personally am going to do it one way, and then I'll kind of show you the opposite sort of approach. And again, they really all should get you to the same outcome. But since we have sort of these stepwise equations given to us, we could actually use these stepwise equations to sort of help us figure out certain things. So for example, they're on the bottom here. So we got these two equations. If I look at right now what I have given to me, I have given to me from this ice table the concentration of my complex ion, which would be this guy. I also have the concentration of my ligand, which would be this guy. And I can see that if I went to the first equation, I really only have this guy given to me at this point. So what that allows me to do, if I wanted to at this point, is I actually can use K2 here to find the concentration of this guy, which was one of the guys that we were asked to find. And I could do that by simply just using the K2 equilibrium reaction. So that's what I'm going to do here. So using the K2 equilibrium reaction, if I write the equilibrium expression for just K2, not the overall reaction, just what's happening in that second equilibrium reaction, we would end up with something like this, divided by this guy times this guy. So why did I choose this one? I chose this one because I have the K2 given to me. I also have, from my ice table that I just did, this guy's number. And I have this guy's number. So that will allow me to really solve for this guy. So if I do that, that will essentially give me, using again K2's value, 3.9 times 10 to the 4 is equal to what we just calculated up on top, 4.29 times 10 to the minus 4, divided by this guy, which is what I'm looking to try to find, and my S2O3, which is 2.86 from my table. Again, here I am not using the overall reaction. I am using specifically the equilibrium constant that goes with the second step and the associated reaction for the second step. That is why I don't need to square the 2.86, because I'm not using the overall reaction. I'm using just the second equilibrium. Just like before, these two guys basically swap spots. And that would give us AgS2O3 minus is equal to 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the 4 times our 2.86. And that will now give me 4.29 to the minus 4 divided by 3.9 to the 4 and 2.86. That is going to give me, if you got some scientific notation going on your calculator, maybe something like 3.8 times 10 to the minus 9 molar. And that would be our concentration. We'll add it to our list up here of this guy, sort of our intermediate complex ion that was being formed. If you don't have your calculator scientific notation, you would get like a bunch of zeros with a 4 at the end. And that's why it's actually 3.8. Any questions up to that point? Now remember that ultimately we also want to know what is the silver concentration. And by doing this sort of stepwise fashion, which you can do here, I have now, by solving for K2 there, I now know this guy's concentration, and I previously knew this guy's concentration. That is now going to open up the door for us to figure out what silver's concentration is. Again, if you want to use just the K1 expression and the K1 equation. So that's what I'll do right now. Again, because they gave it to me broken up like this, and since they're all equilibrium constants, you can basically do this as equilibrium concentrations. So now using our K1 expression, which would be the concentration of this guy here, divided by silver's concentration, and our S2O3, 2 minus, again equaling our K1, 7.4 times 10 to the 8. I could do this, as I just mentioned, because now I have both of those information. Putting those numbers in gives me up on top what we just solved for, 3.8 times 10 to the minus 9. And divided by our silver, which is what we're looking for. and our 2.86. Again, I don't have to square it or anything like that because I am using this equation right here that goes with that K value. Just like the other one, these guys again basically switch places. That gives us silver is equal to 3.8 times 10 to the minus 9 divided by 7.4 times 10 to the 8 and 2.86. And if I do that, we end up with 1.8 to the minus 18, which would be our silver concentration. And it would make our assumption pretty correct as well. That is an extraordinarily super small value of free silver that's still floating around this solution, as we would expect here, because that formation of that complex ion is really, really favored. First off, any questions on those steps there? Now, I did mention before that alternatively, you could approach this problem slightly different if you wanted to. And you could approach it very similar to what we did kind of in the first example. So what I'm going to do is just kind of show you that and just show you that, you'll end up with really the same answer. So I just want to get that number there. If you remember, we added these equations together and we got 2.9 to the 13 for our KF value. So looking at our reaction here, our overall reaction, which is silver plus our 2s2o3 2 minuses. Again, pretty much heading in one direction here, even though it is reversible. And if we were to do our KF for this, it would be our product for the overall reaction divided by our silver and our S2O3 2 minus squared. I am squaring it because now I am dealing with the overall reaction, and that would equal the value I just mentioned, which was 2.9 to the 13. We obviously would run through our ice table just like we did before, so I won't rewrite it, but if you remember from the same ice table we just did on the previous page, we zeroed this guy out. We ended up with 2.86 for this guy, and we ended up with 4.29 times 10 to the minus 4. At this point, once you did that first ice table, even like we did in the previous problem, you absolutely could use the overall KF expression to actually solve for silver first if you wanted to. We would do that the same way. We would then assume that silver is X, even though almost 100% of it's in that complex ion. I'll draw the smallest arrow I can, super small amount is going to head back in the other direction. So just like we did before, we can basically go into our KF at this point, which would be 2.9 times 10 to the 13 would equal our 4.29 times 10 to the minus 4 divided by our silver concentration and our 2.86. Again, here we would square it because of that. Again, these two guys are basically going to swap places, and that basically will give us 4.29 times 10 to the minus 4 divided by 2.9 times 10 to the 13, and our 2.86 squared is equal to our silver concentration. I'll cross it out there. And if we do that, surprisingly enough, hopefully not surprisingly enough, but we end up with, I hope so, if I get to actually get my calculator to hit the right numbers there. We end up with 1.8 times 10 to the minus 18 would be our silver concentration. Now again, that number is the exact same number we hit here by using the individual reactions. So clearly here, you could take the same approach at this point. And now that you would have the silver concentration, you could use the K1 to really find the concentration of the other guy there, which was the AgS2O3 minus. So you will have to, even though you kind of go this way first, you will have to then go into our K1, which was again our silver, I believe. Where's that there? Which was our silver ion plus our S2O3 2 minus, going to this guy. And again, you would have to do this because the question asks for this guy as well. So using our K1, just like we did previously, if you kind of went this way first, would give you the same sort of outcome. And again, because they're all equilibrium expressions, they're all equilibriums, this K1 was 7.4 times 10 to the 8 is equal to this guy's concentration, which is what we're looking for. And now using the values we just calculated, 1.8 times 10 to the minus 18, by calculating silver's concentration first, and our 2.86, basically just multiplying everything to the other side. That's on the bottom. Gets you 3.8 times 10 to the 9 minus 9 molar is this guy's concentration, which again, as you can see, is the exact same concentration we got doing it the first method. So what this really demonstrates is a couple of things. It demonstrates obviously the assumptions that we're making in terms of our complex ions seem to be correct, as we're getting very, very small amounts of our metal when it reaches equilibrium. And it also does show you, it gives you a little variety, especially in problems like this where they ask you what is everybody's concentrations. If they give you this sort of stepwise fashion, as long as you have some equilibrium concentrations, you could go into each step individually if you like and solve for what you're looking for. You can take the approach here where you take the overall reaction, use the overall reaction, and kind of work your way backwards. Any questions on sort of the alternative approach? Again, you can see they both get you the same spot. Okay, so in these stepwise ones, it does give you a little bit of some options in terms of how you solve it. All right. So let's look at one last sort of example involving complex ions and really sort of a mixture of things that occur. And what I mean by that is, let's take a look at this one here. We want to calculate the molar solubility of silver chloride in 1 molar ammonia. So we have our two sort of reactions that are happening. We have our KSP reaction, which is our silver chloride breaking apart into silver ions and chloride ions. We also have our complex ion formation here of our silver and ammonia coming together to make our diamine silver 1 ion basically happening. So basically we were kind of mixing a couple of things here. We're mixing kind of our insolubility with our solubility of complex ions. So what we're going to do is, to start off with, is really just add both of these reactions together and kind of see what are we getting in terms of the overall reaction. So if we did that, we could simply add these guys together. When we add these guys together, the silver ion on the left and the silver ion on the right will actually cancel each other out. That will leave us with really the overall reaction that we're talking about here, which is silver chloride plus, you add some ammonia to it, will make this complex ion. And you'll have some chloride that's around. Right? Now, I added these reactions together to get my K value for this reaction, my K overall here. I need to take the KSP times the KF. You may be asking yourself, can I do that if they're not the same? And the answer is yes, you can, because they're both equilibrium constant values, right? So even though one's a KSP and one's a KF, they're both ultimately just equilibrium constants, no different than when you take a Ka times a Kb to get a Kw, right? So same idea here. You could definitely multiply these guys together. And if we do that and multiply these guys together, we will get an overall K for this reaction of 1.6 to the minus 10 times 1.5 to the 7. Remember, we multiply here to get the K, not add. So 2.4 times 10 to the minus 3. Any questions on that so far? Now, the key here is when we think about what we're looking for the molar solubility, right? So molar solubility really makes us think about like a KSP type of ice table, right? And in a KSP type of ice table, molar solubility is S, right? That is what molar solubility is. So ultimately, that is what we are trying to find here. And that is really what we should approach this problem like, is really like how we've done a KSP table previously. So that's the approach we want to take here, really, because we're looking for that molar solubility. And that really is this overall reaction that's happening here. So using that overall reaction, we're going to take our silver chloride plus our couple of ammonias, and again going to form that complex ion and some chloride. And we saw that the K for this guy going to be 2.4 times 10 to the minus 3. So approaching this like a KSP problem, first off, just like before, this is solid. I'm not going to worry about this guy. This guy, we actually do have an initial concentration. Remember, we are starting with 1 molar of this guy. So this is not 0 in this case, slightly different than what a normal KSP type problem. This guy actually will have a value, and it is 1. This guy will be 0, and this guy will be 0. Just like normal, we're going to use S here. This would be minus 2S plus S and plus S. Remember again here, S being our molar solubility. That means when we reach equilibrium here, we're going to have 1 minus 2S, S, and S in this case. Any questions on that so far? Okay, so what we're trying to find now, right, is sort of our molar solubility. So we are going to use our K expression here. Again, slightly different than a normal KSP, because if we look at this, this would be our product. Divided, or actually we got 2 products, Cl minus, there we go. And divided by our reactant, which in a normal KSP, we don't really have a reactant, but in this case, we actually do. This guy, again, not included because it is a solid, and that would equal our 2.4 times 10 to the minus 3. Just like a KSP, we put our guys in, and we're going to solve for S. So putting those guys in gives us basically S times S divided by 1.0 minus 2S squared is equal to 2.4 times 10 to the minus 3. At this point, hopefully you recognize it is a perfect square on both sides. So might as well take a big old square root there and a big old square root there. And when we do that, we end up with S over 1 minus 2s, and important to remember to actually take the square root of the other side there. So the square root of 2.4 to the minus 3 ends up being something like, call it 4.9 times 10 to the minus 2, since I still have my guy in scientific notation, or 0.049. We're going to multiply everything on the bottom to the other side. That's going to give us 0 is equal to 4.9 times 10 to the minus 2 minus 9.8 times 10 to the minus 2s. Bringing this guy to the other side will give us basically 1.098s is equal to 4.9 times 10 to the minus 2. Solving for s here, going to get us we'll call it, we got there, 4.5 to the minus 2 molar. Any questions on that there? So in this particular case, that S, remember, is really this guy's concentration. This guy's concentration, if you put it in there, how much NH3. But even though we really didn't put anything in our table, right, it is a 1-to-1 relationship back to this guy. It's really a 1-to-1 relationship back to this guy. That is really the molar solubility of silver chloride in ammonia, basically moles per liter. Any questions on that there? Now, what does that number really mean? Well, if you remember, perhaps in water, in an earlier example for silver chloride, we saw that the molar solubility of silver chloride in water is 1.3 times 10 to the minus 5 molar. Silver is 107.9, chlorine is 3545. Get my calculator out, scientific notation. There we go. It's a 143.4 grams per mole. So gram's sake, if we want, in water, if we times this by 143.4 grams per mole, we would end up with, in pure water, as I think we saw earlier, you would be able to dissolve 0.0019 grams per liter of silver chloride. How much better is it in ammonia? Well, let's see. If we times this guy by 143.4 grams per mole, basically converted it into grams per liter, 4.5 to the minus 2 times 143.4, you could dissolve 6.45 grams per liter. I would say that is a fairly big difference in the amount of silver chloride that would dissolve in water versus in ammonia. Any questions on that? So what does that really mean? This definitely shows you that the formation of a complex ion, when a good ligand is present, is favored for sure. Any questions on any of that there? You might also recognize this reaction as something that you did in group 1 of qualitative analysis. If you remember, the test for silver is you make some silver chloride, which is that white solid, right? What do you do at that point? Well, you add some ammonia to it. Yeah. And when you add ammonia to it, what do you see happen to that white solid? Well, we see that white solid disappear, and it disappears because the formation of this complex ion we're talking about is favored because of our KF and stuff like that, right? And that's why we see that white solid, which I'll draw as red, we'll just imagine. When we add the ammonia in group 1, it forms this complex ion. So in our test tube, all looks very solution-y, because we know from our conversation here of KF that pretty much the safe assumption is any free silver that's kind of in there basically will hook up with the ammonia. It is such favored that it's able to basically free up the solid silver chloride that's in there with that chloride, and it decides, I don't really want to be with the chloride. I much rather be with the ammonia coming in to form that. And again, we see that disappearance of that solid that was there originally. If you remember, the last part of that test is you had some nitric acid, right? Nitric acid is a lot of H plus and ammonia going to basically get rid of the ammonia and free up your silver ion again, making it really acidic, right? So it can cause that ammonia basically to become NH4 plus and kind of free up itself from the silver. And it's going to decrease the amount of NH3 that was present in that solution, liberating the silver. But we see the solid come back. Why do we see the solid come back? Because if you see right here, there's still chloride floating around that solution. And these two guys can now come back to our silver chloride again as a reddish white solid, not really a white solid. We'll just draw it red, but it's able to recombine for that. So this is actually what we just did in that problem, is essentially what is happening when we did in group 1 that test for silver. We made the solid, we forced the equilibrium all the way to the right and the formation of that complex ion, which is definitely favored because of the KF value, and essentially so much favor that we're able to essentially rip out the silver from the solid, and it would want to hook up with the ammonia and make that complex ion. The only way we could really free up the silver from that complex ion is getting rid of the ammonia that's in there by making the solution really acidic, going to free up our NH3 really into NH4 plus, and by process freeing up the silver ions, that then we'll have really no other option but say I'm sorry to the chloride and say I'll come back. And they come back and basically make that white solid again. Any questions on that? All right, well, that is this little bit of the chapter, KF, complex ion formation. Any questions on that? Again, a reminder that this is back to chapter, I believe, 16, right after KSP. And that now leaves us really just one chapter to go, which is kinetics, and then it's all over at that point. Any questions on anything we talked about here in terms of lecture today?